Welcome to this section for chapter 5. So there's a final probability distribution, final discrete probability distribution that I had forgotten to talk about. This is the hypergeometric distribution. So it is related sort of to the binomial distribution. Remember, in the binomial distribution, we had a situation where, first of all, you have you have two possible outcomes. Yeah, so you have these conditions. You have two possible outcomes. You have n trials. Then you have the probability of one outcome. So probability of one outcome is P. Then the other outcome, then the alternative occurs the probability of 1 minus P. Then, of course, you had independent. The trials are independent trials. Then you had what you call a stationarity assumption. Stationarity assumption. So maybe if you want to conserve the order in a book, it means this is actually condition number 4. It's actually condition number. So this is not really a condition. Yeah. So you have these 4 conditions in a binomial distribution. So we basically assume that the trials are independent, and you have a stationarity assumption. But there are situations in which this assumption does not hold. For instance, if you are picking from some group if you're picking out of, let's say, a basket, and then you're not replacing, so that means that the probability of the trials is going to actually affect probability is going to change with each trial. So the trials are not really independent. So this is what I am talking about. So if you have some container, for instance, let's say you have a container. Try to draw a container. So let's say you have a container, right? Why isn't this working for me? I want to get one of those. Yeah. So yeah, so I have one of those, and then let's say we have this container over here, right? And let's say we have a bunch of balls in a container. I'm going to get a bunch of blue balls. Okay, so I have a bunch of blue balls in there. Maybe I can just copy and paste this. Right. So I have a bunch of blue balls in my container, right? So let me get a bunch of maybe red balls in the container. So if I'm picking from a container and I'm not replacing, right? Because before the binomial distribution, you have the same probability. For instance, if you're flipping a coin, because you're always going to generate heads or tails with the same probability of 0.5 if you're using an unbiased coin. But in the situation where you are picking maybe elements from a container, then it's going to be a bit different. Let me try to paint. It's going to be a bit different. Because if I pick from this container, which has how many balls? 1, 2, 3, 4, 5, 6, 7, 8. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this container has 11 balls. Yeah. So if I want to see the probability of picking red balls, so the first time I do it, how many red balls do we have? We have 1, 2, 3, 4, 5, 6. So we have, so first time I pick is going to be 6 out of 12. But if I do this twice, yeah, so the probability is actually going to be less. So the second try, probability of picking a red ball, if I picked a red ball on the first try, then the probability of me picking a red ball on the second try is actually going to be 5, because now there's one less ball because I picked a ball and I did not replace the ball. So next time I pick is actually going to be 5 over 11, because now I only have 11 balls in the box. If I do this 3 times, then the probability that I actually pick a red ball is going to actually be now 4 out of 10, because we actually have less. So you can see that the subsequent trials are being affected by the previous trial. So the result that I get in the subsequent trial, alternatively, if I actually did pick a blue ball, then the probability is going to be 6 of 12, because we still have 6 red balls. On the first try, it's going to be 6 of 12. Then on the second try, if I did pick a blue ball, then it's going to be 6 of 11. If I still pick a red ball on the third try, then it's going to, on the second try, then I'm going to end up with still 6 of 10. So you can see in this situation that actually the probability that I do pick a red ball is actually going to be changing. So to actually get the probability analytically means, you know, with if I come up with a formula to actually obtain the probability that I do pick a red ball given n tries. So given n tries, if I want to see the probability, for instance, that I pick 3 red balls, yeah? If I pick 3 red balls in, say, 5 tries, so let's say the probability of picking, I forgot to give this a caption. So this is what we call a hypergeometric distribution. Yeah. So if I want to see the probability that I actually do pick of picking 3 red balls, in n tries. So really, this is going to be, so if I pick 3 red balls in n tries, so number of tries is n, right? Let me just start with a general formulation. Probability of picking x red balls in n tries, so number of tries is n. So this time, number of successes is going to be x. So number over in the general in the general container. So overall in the container. So the number of overall, let me call it overall successes in the container, or number of red balls in this case is going to be R, right? Then total number so the total number overall is n. So that is, in this case, n is 11 because we have 11 balls in a container. Then we have x, and in this case we say our x is going to be the number of say the number of red balls that we want to pick. So if you want to pick this in n tries, we'll try to set a probability that we actually pick x red balls in a container containing n balls, and then we have and of those n are red, right? So this is actually going to be so we're basically asking how many ways can you pick n? How many ways can you pick rather x? How many ways can you pick x out of R? It's really what you're doing. How many ways can you pick x successes, x red balls out of R red balls? Yeah. So this is really going to be the combination. So we have this combination notation. So let's just insert a new equation over here. So we insert the new equation. So I did say I didn't like this notation very much because it's a bit confusing. So you're looking for the combination. So you're looking for this combination over here. Yeah, but maybe just use the notation that is used more frequently in the book, which is actually going to be, so insert the equation. I want one of the, let me see, I want a bracket, yeah. So I want one of these. I want one of these. So yeah, so we want to see how many different ways can you pick X red balls. We have R red balls total, but we want to see how many different ways can you pick X red balls from R red balls. So that is this combination. And then when we get this, we have to multiply it by the number of ways that you can actually pick. Because when you pick X red balls, what happened? So when you pick X red balls out of n tries, what you're really doing is that you're going to pick, because you have n tries, right? That means you're going to pick n minus x blue balls, right? You're going to pick n minus x blue balls because you're picking n times, right? So if you pick n times and you pick x red balls, then it means the remaining picks are going to be blue, yeah? So then you're going to find out, but these blue balls that you're picking, you're actually picking them out of n minus r blue balls, because remember n is the total number of balls, right? So if you pick r red balls, it means you're going to pick n minus r blue balls, right? If you pick r red balls, you're going to pick n minus r blue balls. If you pick x, and these red balls, you're actually picking them out of the x, rather. Let me say that again. If you pick x red balls, it means you're picking n minus x blue balls, and the x balls, you're picking them out of r balls, and the n minus x blue balls, you're picking them out of n minus r balls. So this is actually the number. So how do we express this as a number of so how do you express this as a probability? This is quite simple. We just need to compute the total. So let me just get that. Oops, I need to come out of this. So we need an equation. I just need to get a fractional, yeah. So this whole thing is actually going to be the numerator. So that's actually the number of different ways that you can pick. This is the number of different ways that you could pick X red balls and n minus x blue balls given n trials over a population of n, where r balls are red and n minus r balls are blue. And then the denominator is going to be the total ways that you can actually pick n balls, the total different ways that you can pick n balls from n lowercase from n uppercase, right? So let's just look at the equation. Want to insert an equation. Why is it doing this? Okay, so so we need a bracket. So we need one of these. So basically, this is the total number of ways that we can pick n lowercase red balls from n uppercase balls. So if you go back to our situation, we say we have our n is 11 uppercase. So this is the total number of balls. Of those, the red balls, did you say there are 6? Yeah. So red balls are 6. So that means then we have 5. Let's say we have 5 trials. So 5 different picks, and then we are interested in finding the probability that we pick exactly 3 red balls. So that means we are interested, if we apply this equation over here, we are, if we apply this equation now, R becomes 6, and out of this 6, we want to pick 3. We want to pick 3 red balls. Then N uppercase, it's a bit, so N uppercase, just a minute. So N uppercase is going to be the total number of balls, which is 11 in our case, and R is the number of blue balls, right? Which is 5. R is 5, and then N minus X. So if you have 5 picks and then we want 3 red balls, it means that the remainder is going to be then you're going to have two blue balls, right? Then the uppercase N is 11 again, and the number of picks is going to be 5. So this is essentially what we have over here. So this is going to really be it's a whole bunch of calculations. Let's see. So you want the fraction. So it's going to be, so on the top we have another fraction. So a combination this is actually 6 factorial. 6 factorial into 6 minus 3 factorial, which is 3 factorial. So that is 3 factorial. And then we want to multiply by so that's going to be another it's going to be another fraction, so that it's going to be 5 factorial. 5 factorial into oh, I forgot something here. So it's 5 factorial into 2 factorial times 3 times 5 minus 2 factorial, which is 3 factorial. So we say this is going to be 6 factorial over 6 minus 3 over 3 factorial. 3 factorial times 6 minus 3 factorial, which is still 3 factorial. So the denominator is going to be 11 factorial. So we need another fraction over here. So it's going to be 11 factorial. 11 factorial over 5 factorial. 5 factorial times 11 minus 5 factorial, which is 6 factorial. So this is basically, so you work this out. When you work this out, let me see, 6 factorial over 3 factorial minus 3 factorial, I think that is 6 by 5 by 4. So if you get rid of the factorials here, 6 by 5 by 4, this is basically 6 by 5 by 4. Get rid of one factorial, and this 3 factorial is basically 6. So you get rid of that, so that leaves you 5 times by 4, which is 20, times so 5 factorial over 3 factorial, that is 5 by 4. So you're gonna have 5 by 4. Just a minute. So you're gonna have 5 by 4. Then divided by 2 factorial, so that's basically 5 by 2. So you're gonna have 10. Then 11 factorial, that's gonna give you 11 by so that's basically 11. So that's 11 by 10 by 9 by 8 by 7. So you could actually get rid, oh, what's this? So you said 11 by 10 by 9 by 8 by 7. Then we can get rid of the 6 factorial. So then we have the 5 factorial. So what do we do? So 5 factorial, 5 by 4. Just try to simplify. 5 by 4 by 3 by 2. So if you do this over here, get rid of 5. You get rid of the 4. You get rid of the 3. You get rid of the 2. So you have this 20 over 200 divided by actually I could have just done this in a calculator immediately, but let's see. So you have 200 divided by 11 divided by 6 divided by 7. Let's see what you get. So apparently your probability is going to be something like 0.43. So you have 0.43. Yeah, so this is a probability that you actually get free, exactly free red balls. Maybe let's look at the example that we have over here, and we see if we actually do get the correct answer. So in this situation we have this kind of situation. N is 12, Ri is equal to 5, yeah, so R is equal to 5. So you have electric fuses produced by Ontario. So each box contains 12 units, and then in the 12 units you want to inspect randomly and select 3 of 12 fuses in a box. For testing, if the box contains exactly 5 defective fuses, what's the probability that you find exactly one of the 3 that you've picked out to be defective? So here the X success actually means that you are picking a defective fuse. So we say you have if you get our equation back, so this is our equation, insert the equation. So you want to have so the top is going to be oh, wait a minute, let me just I got rid of it. So anyway, let's do this again. So basically you want to have one of these into one of those. Let's just get the equation back. So you basically have your X of R, then you have your n minus X over n minus R, then you have then you want to pick how many, then you have your n of n. Yeah, so this is basically going to give you this following form. So we know that R is going to be 3, and you want to pick out we want to pick out 1, and n minus R, because you have 12, right? So 12 minus how many defective? one of 3 fuses are defective. 12 units, 12, if the box contains exactly, let me just zoom this down a bit, exactly 5 defective fuses. So it's actually 5. It's actually 5, and you want to pick out exactly 1. What's our probability we find exactly 1 of the 3 fuses defective? Yeah. So R is 5, and then X is so then N minus R is 6. Yeah. So the ones that actually work are 6. Then N minus X is what? N minus X is going to be, so how many times are we picking? 3 times, so N minus X is actually 2. So N minus X is 2. And then N overall, we actually have 12 fuses. And the number of tries is actually 3. The number of tries is actually 3. So let me just check, is that the correct form? So 12, 3, 5, 1, 7, 2. Oh, okay, so this was N minus R. Okay, this had to be 7, right? This had to be 7. I'm looking at this part over here, just to see if you're getting the right equation. Yeah, so everything else, so what remains is for you to actually calculate this value over here and then get the correct answer, but this is the correct form of the equation. So that's it for the last part of chapter 5.